Avionics are the brain and nervous system of an aircraft. They manage communication, navigation, control, and safety, guiding every flight from takeoff to landing. This presentation highlights the role of avionics and the subsystem design. This presentation is divided into 3 key sections. First, we'll look at the role of avionics in civil aircraft and how they ensure safe and efficient flight operations. Next, we'll explore their role in military aviation, where technology enhances mission capability and survivability. Finally, we'll examine the design of avionics subsystems, the engineering foundation that makes all of this possible. Let's start with the role of avionics in civil aircraft. These systems are vital for safe, efficient, and well-coordinated flight operations from takeoff to landing. Avionics form the backbone of modern civil aviation. They enable pilots to monitor, manage, and control every aspect of a flight, ensuring both safety and operational efficiency from takeoff all the way to landing. The Flight Management System, or FMS, is at the heart of modern cockpit automation. It calculates the most efficient flight path, manages navigation, and optimizes fuel usage, all while reducing pilot workload through automated flight planning and continuous monitoring. Autopilot and auto-landing systems help maintain a stable and precise flight. They manage altitude, speed, and heading, and even enable automatic landings in low visibility conditions, improving accuracy and greatly reducing pilot fatigue. Navigation and communication systems are essential for safe and coordinated flight operations. They include technologies like GPS, VOR, ILS, and satellite communication, providing precise positioning and ensuring constant contact with air traffic control throughout the journey. Safety and awareness systems play a crucial role in protecting both the aircraft and its passengers. The weather radar detects storms and turbulence ahead, helping pilots adjust their routes. The Terrain Awareness and Warning System, or TAWS, alerts pilots to possible ground collisions. And the Traffic Collision Avoidance System, or TCAS, prevents mid-air collisions by warning of nearby aircraft and suggesting evasive actions. Next, let's look at the role of avionics in military aircraft. Here, avionics go beyond basic flight control. They enhance mission effectiveness, situational awareness, and combat readiness in demanding environments. Military avionics go far beyond basic flight control. They're engineered to enhance mission effectiveness and ensure survivability in demanding combat environments. These systems provide pilots with superior situational awareness, precise targeting capabilities, and advanced self-protection measures that can make the difference between success and failure in a mission. Advanced sensor integration gives modern military aircraft a decisive edge. Multi-mode radar systems detect, track, and classify targets across both air-to-air and air-to-ground missions. Infrared and night vision sensors extend this capability into darkness and poor weather, allowing operations to continue when visibility is limited. Electronic warfare systems are vital for defense and survival in hostile airspace. They detect and counter enemy radar and missile threats using techniques such as jamming, radar warning receivers, and countermeasures like chaff and flares, helping protect the aircraft and its crew from incoming attacks. The helmet-mounted display, or HMD, brings vital information right into the pilot's line of sight. It projects flight and targeting data directly onto the visor, enabling instant access to critical information and precise aiming, all without the need to look down at cockpit instruments. Secure communication and data link systems ensure seamless coordination across all mission elements. Technologies like Link 16 provide encrypted, real-time data exchange between aircraft, ground units, and command centers, enabling precise, unified mission execution. Mission computers act as the aircraft's central brain, integrating and managing all onboard systems. They enable precise weapon targeting, guidance, and controlled deployment by coordinating sensors, flight controls, and fire control logic, allowing complex engagements to be executed accurately and reliably. Finally, let's move on to the design of avionics subsystems. This section focuses on how these systems are engineered, integrating hardware, software, and communication networks to ensure reliability and performance under extreme conditions. The avionics subsystem serves as the central electronic framework of an aerospace vehicle. It enables control, communication, navigation, data acquisition, and mission execution, forming the technological core that keeps everything connected and operational. Designing such a system demands expertise across multiple disciplines, including electrical, mechanical, and systems engineering, to guarantee reliability, efficiency, and seamless performance under extreme conditions. The core objectives of avionics design center on performance, reliability, and integration. First, systems must process data and control onboard functions in real time. They ensure robust communication between sensors, actuators, and flight computers, while maintaining fault tolerance to continue operating even during anomalies. Avionics also integrate mission-specific payloads with general-purpose control electronics, all while meeting the strict mass, power, and volume limitations demanded by aerospace applications. Avionics subsystems are engineered to perform reliably even in the most extreme environments, from the vacuum of low Earth orbit to the thin air of high-altitude flight. Designers must account for two critical challenges: radiation and temperature. Radiation hardness is essential, as exposure to ionizing particles can damage electronic components or corrupt data through bit flipping. To counter this, engineers use radiation-tolerant parts, physical shielding, and software-based error correction. Equally important is thermal stability. Avionics must operate across temperature ranges from -40 to +150 degrees Celsius. Achieving this requires careful material selection, efficient heat dissipation pathways, and designs that prevent thermal fatigue in soldered joints and connections. Vacuum compatibility is a key consideration in avionics design for space applications. Materials must resist outgassing, which can release vapors that contaminate sensitive surfaces and degrade system performance. To prevent this, only space-qualified components, coatings, and adhesives are used, all carefully selected to maintain stability and reliability in vacuum environments. Avionics hardware must endure intense vibration and shock loads experienced during launch and high-stress flight conditions. To ensure durability, components are mounted on rigid structures with vibration-damping materials that absorb mechanical energy. Every system undergoes extensive qualification testing to verify that it can operate reliably under extreme mechanical stress without performance degradation. A well-designed avionics subsystem is built on a modular architecture, where each functional block operates independently yet integrates seamlessly with the whole. This separation of functions enhances efficiency, simplifies maintenance, and allows upgrades or replacements without disrupting the overall system. The onboard computer, or OBC, serves as the central command unit of the avionics subsystem. It handles system-level operations such as telemetry management, command execution, power regulation, and coordination between various subsystems, ensuring that all onboard functions operate in harmony and respond efficiently to mission requirements. Sensor and payload interfaces act as the communication bridge between the avionics core and external instruments. Dedicated interface boards or microcontrollers manage sensor data acquisition, signal conditioning, and analog-to-digital or digital-to-analog conversion. By incorporating parallel processing devices such as FPGAs, these interfaces greatly improve real-time signal handling and reduce the computational load on the main onboard computer, ensuring faster and more reliable system performance. Reliable data exchange among subsystems is fundamental to avionics performance. Communication protocols are selected based on their speed, noise resistance, and scalability. High-speed connections like SPI handle rapid sensor or memory transfers, while CAN networks provide robust, noise-tolerant communication across multiple nodes. I2C offers compact, medium-speed wiring for lower-priority sensors, and UART provides a simple serial link for diagnostics or backup communication. This hierarchical structure ensures efficient bandwidth use and prevents data congestion. Beyond data flow, Avionics design also demands careful physical and logical integration. Engineers focus on electromagnetic compatibility, optimized wiring layouts, and protocol synchronization to maintain stable, error-free operation under all conditions. Component selection in avionics design involves balancing reliability, cost, and customization. Commercial off-the-shelf, or COTS, components are widely used because they're cost-effective, well-tested, and simplify integration. However, they can limit adaptability for specialized missions. Custom components, on the other hand, are developed when unique performance or environmental requirements cannot be met with standard parts. While they demand more testing and validation, they provide greater optimization and control. In practice, the most effective designs combine both, leveraging proven COTS systems for core functions and integrating custom-built modules to meet specific mission objectives. Verification and validation are critical stages in avionics development, ensuring that every subsystem performs reliably under real-world conditions. Environmental testing subjects the hardware to thermal vacuum cycles, vibration, and radiation exposure to confirm durability. Electrical testing verifies power distribution, signal integrity, and redundancy across circuits. Finally, functional testing checks command execution, data throughput, and communication consistency, guaranteeing that the complete avionics system meets its intended performance and safety requirements before deployment. From a systems engineering standpoint, effective avionics design balances innovation, reliability, and long-term adaptability. A modular structure simplifies maintenance and future upgrades, while redundancy provides fault tolerance for critical functions. Integration efficiency minimizes wiring, mass, and complexity, improving overall system performance. Scalability ensures that the architecture can accommodate evolving mission requirements or additional payloads. Ultimately, the goal is to merge emerging technologies, such as FPGAs and miniaturized sensors, with proven safety standards, achieving a design that is both forward-looking and dependable. I hope this presentation gave you a clear understanding of their vital role in both civil and military aircraft. Thank you.